Welcome back, friends, to this another session of Smart Crack NEET series 2022. And we are going to discuss about the electric charges and fields today. Okay, so this is first chapter of class 12 physics, and many students were demanding for starting the class 12 physics, and we have finally started. Okay, so let's begin. So, first of all, these are very common things. So what is an electric charge? So it is property of matter that causes the matter to experience a force when kept in electromagnetic field. Okay. Then there are some properties of charges, and sometimes there can be a direct question. Okay, there can be a direct question on properties of charges. So first property is charge on the body. It is quantized. Okay, electric charge is always quantized, and it always comes in the integral multiple of E. So what is E? E is the charge on electron. Okay, so we know that the charge on bodies appear because of what? Transfer of electrons, either from body to another body or from some another body to that body. Okay, and that's why the charge on any body will be in integral multiple of the charge on electron. Okay, so charge is always uh, the excess of electrons or lack of electrons. All right. So that is quantization. Next is additivity. So charges add like scalars. Okay. After that, next thing is conservation. So if you consider any isolated system, even if you consider the universe, okay, so total universe, if you consider it as an isolated system, so the total charge in any isolated system will always remain conserved. So charge cannot be created, it cannot be destroyed. Total charge, it will remain conserved. Okay, so after that we have Coulomb's law. So we know that like charges repel each other, unlike charges attract each other, and the force of attraction or repulsion between two charges, it is given by the Coulomb's law. So what is Coulomb's law? So Coulomb's law says that this force of attraction or repulsion between the two charges, it is directly proportional to the product of two charges, and it is inversely proportional to the square of distance between them. Okay, and if we remove the proportionality sign and put an equality sign, a constant will come in, as we know. So that constant k is given by 1 over 4 pi epsilon naught, where epsilon naught is called as permittivity of free space. So if two charges are kept in free space, the constant will be 1 over 4 pi epsilon naught, and its value is given by 9 into 10 raised to 9 Newton meter square per Coulomb square. So we need to memorize this value. Okay, not the value of epsilon naught, value of this constant k when charges are kept in free space. Okay, after that, so if you move from free space to some another medium, what will happen? This permittivity will change. Okay, so if you take ratio of permittivity of medium to permittivity of free space, you get a quantity called as dielectric constant. Okay, so what is dielectric constant? This is small k. Okay, it is permittivity of a medium divided by permittivity of free space. So k is equal to epsilon, which is permittivity of a medium, divided by epsilon naught, which is permittivity of free space. Okay, so then now this was Coulomb's law in scalar form. If you want it in vector form, so it looks like this. So force acting on Q2 due to Q1. Okay, so I didn't draw Q1 and Q2 over here. So let's say this is Q1 at position vector R1. This is Q2 at position vector R2. Okay, then force on Q2 due to Q1, it is given by F12 bar, and it is 1 over 4 pi epsilon naught Q1 Q2 upon R12 square. R12 is the distance between them, and it is directed. See how to find direction of this force. So you draw a unit vector directed from first charge to second charge. That means first charge is the charge which is exerting the force, and second charge is the charge on which the force is acting. Okay, so you draw a unit vector from charge which is exerting a force to the charge which is experiencing that force. Okay, so R12 bar. So unit vector from 1 to 2. Okay, and now see, if both charges are positive, what will happen? So if both charges are positive, Q1 times Q2 will be positive, and the force will be directed along that unit vector. Okay, if both charges are negative also, then the product will be positive, so the force will be directed along that vector. That means there will be repulsion, so q2 will be pushed away by q1. Okay, but if one charge is positive, another one is negative, then product of two charges will be negative, and that means the force will be in opposite direction to that of r12 bar. So r12 bar is like this. Okay, from q1 to q2, that means q1 is repelling q2. Okay, if force is along that line. But if, let's say, force is in opposite direction, when will that happen? When the uh, signs of two charges are opposite, one is positive, another one is negative. So the force is like this. That means from q2 to q1, that means q1 is attracting q2. Okay, so force acting on q2 due to q1 will be towards q1. That means q1 is attracting q2. All right, so this vector is important. It is directed from the charge which is exerting the force on the charge which is experiencing the force. All right, okay, so F12 bar is the force on q2 due to q1. Okay, so see the order of 1 and 2 over here. Okay, 1 comes first, 2 comes later. That means the force on which, the charge on which the force act, it comes later. Okay, so it is 1 to 2. All right, after that, next is superposition principle. So what does superposition principle say? If you have n number of charges and you want to find force acting on any one charge due to all the other charges, then what do? Just take force on that charge due to all other charges individually. Okay, so you take force due to one charge, force due to second charge, force due to third charge, so on and so forth, force due to nth charge, and add it up. Okay, vectorically, because force is a vector. So superposition principle says that force on any charge due to all other charges is equal to force on that charge due to, let's say, second charge, plus force on that charge, force on first charge due to third charge, plus so on and so forth, force on the first charge due to nth charge. Okay, so this is simple. Superposition principle just says that force acts vectorically, and that we know because force is a vector quantity. All right. So next term is the electric field. Okay, so we are moving very fast over here because, yeah, we have very little time. So electric field. So what is electric field? So now, if you consider the region around an electric charge where the effect of that charge can be felt, so that region is known as the electric field. Okay, and electric field has got some magnitude, so we find out magnitude of that effect. Okay, and how do we find that? So what will happen when you keep another charge in presence of this charge? There will be some force acting on the another charge. Okay, so what do is, let's say we want to find out electric field due to q, capital Q. So what do? We bring some other charge, let's say small q, and we keep it, let's say, here at distance r. Okay, so we find force on this. So what will be force? It is k 1 upon 4 pi epsilon naught, okay, into q or r square, and then we divide that force with this small charge. Okay, this is called as test charge. So the electric field at distance r due to this charge will be what? The force experienced by the test charge, which is F. Okay, force experienced by test charge, this charge, divided by that test charge. Okay, so this gives us the magnitude of electric field. All right, very simple. So electric field due to a single charge, one charge, is given by what? 1 over 4 pi epsilon naught into q over r square. Okay, then now next thing is the electric field lines. So what are electric field lines? So it is the path along which the unit positive charge will move when kept in some electric field. Okay, so let's say you keep a unit positive charge. Okay, 1 unit of positive charge over here, and this charge is positive. So in what direction this charge will move? It will move along this direction. It is pushed radially outwards. Okay, it gets repelled, so it is pushed radially outwards. Alright, so that line will denote what? The electric field at that point, and that line is known as the electric field line. Okay, so after that, there are some properties of electric field lines. So what are those properties? So they start from positive charge and end at negative charge, because force is from positive to negative. Okay, so let's say you take some positive charge over here, plus q. What will happen? And you take some test charge, then the electric field will be directed from this q to that test charge. Okay, but if you take a negative charge, so this is because what? Force is directed like this. Okay, the test positive charge, it is pushed by the positive charge. But if you take some negative charge, okay, let's say minus q, then what will happen? So it will attract this test positive charge, and the electric field will be like this. Okay, so now if you remove this test positive charge, and if you just want to see how will the electric field in that region look like, so it looks like this. Okay, directed from plus q to minus q. Okay, so electric field lines start from a positive charge and they end at a negative charge. Very simple. Okay, now if you draw a tangent, to the electric field lines, they give the direction of electric field at any given point. So let's say you draw some electric field lines, okay, like this, and you draw the arrows, okay, showing from where they are originating and where they are going to. Okay, and then if you want to find out the electric field at any particular point, let's say you want to find out electric field at this point, so what do? You will draw a tangent, okay, to electric field line at this point. So let's say this is a tangent, and this tangent will give you what? It will give you the direction of electric field at that point. Okay, so simple. Then the two electric field lines never cross each other. Why so? It's because, let's say they cross. Okay, let's consider a contradiction. So let's say two electric field lines cross. So one is like this, another one is like this. And we saw in previous case that the tangent drawn to electric field lines at any given point gives the direction of electric field at that point. So if you consider this point, what will happen at this point? If two electric field lines cross, then one electric field line says that if you want the direction of electric field at this point, draw a tangent over here, okay, which will point in this direction. I will draw with some other color. So draw a tangent over here. And another electric field line says draw a tangent over here. Okay, so it's like this. All right, so the direction of electric field as shown by two electric field lines will be different, and that cannot be possibility. Okay, that can't be a possibility. And that's why the two electric field lines cannot cross each other. So because if they cross, that means they will show the two different directions of electric field at a point, but the electric field can have only one possible direction at any given point. Okay, so the two electric field lines never cross each other, and they also do not form closed loops. Okay, so electric field lines don't form closed loops. So if they form closed loop, what will happen? So you don't know where they are originating from and at which point they are ending. Okay, so you don't know what is the source of those electric field lines, right? So that's simple. Those are properties of electric fields, and there can be some question on properties of electric field lines. All right, so after that, next thing is the electric dipole. So what is an electric dipole? So electric dipole is a positive charge separated by a same amount of negative charge. Okay, so plus q, positive charge separated by same amount of negative charge by some distance. Okay, and this distance, so we are indicating that distance by 2 times a because it is convenient to do so. Okay, so this is the midpoint of this dipole. The O is the midpoint. So distance from plus q to O and distance from minus q to O is what? It is A. So this total distance is A plus A. All right. So we'll just memorize this formula. Okay. So E equals to 1 over 4 pi epsilon naught into 2p upon r cube. So this is for an axial point and for an equatorial point. Okay. So the magnitude of electric field is equal to, this is the formula, complete formula, but in most of the cases we don't need this. What do we need is this formula, okay, where we neglect the size of the dipole. Okay, we neglect size of the dipole because the distance of the point where we want to find out the electric field, it is very large compared to size of the dipole. Okay, so we'll neglect this, and what do we get is this formula. So if you compare these two, okay, so electric field along the axis of the dipole, so you have 1 over 4 pi epsilon naught into 2p upon r cube. Electric field upon at the equatorial point, it is E equals to p divided by 4 pi epsilon naught r cube. So E axial is equal to what? In magnitude, it is 2 times of E equatorial. Okay. So see, here we have E equals to 1 over 4 pi epsilon naught 2p upon r cube, and for equator we have p upon r cube. 1 over 4 pi epsilon naught is there. Okay. So see, forget about the direction. The direction is opposite. Okay. In this case, it is along dipole. That means from plus q to minus q for axial case, and in this case it is from minus q to plus q. Okay. So it is along the dipole means from minus q to plus q, and in this case it is from plus q to minus q. It is in opposite direction of the dipole, but the point to be memorized is electric field along the axial point is 2 times the electric field along the equatorial point. Okay, so is that thing clear? Yes, no? All right, so let's move on to the next point. So next point, I'm sorry. Next point is torque on dipole in uniform electric field. So you have a dipole and you keep it in some electric field. Okay. So this is the dipole and you have kept it in electric field. So there will be some torque acting on it because there is a negative charge and a positive charge. So negative charge is pulled by the electric field. Okay. So force acting on negative charge is in same, it will be actually, if I draw plus q and minus q, I will just change it because force on the positive charge will be in direction of the electric field. Force on the negative charge will be in opposite direction of the electric field. Okay, so positive charge is pushed by the electric field, negative charge is pulled. All right, so these are two equal and opposite forces. So we know if we have two equal and opposite forces, they form a couple. Okay, so equal and opposite forces separated by some distance, they form a couple. And what does a couple do? It rotates the thing on which it is acting. Okay, the thing which is on which the couple is acting. Okay, so it creates some torque. So that torque is given by what? It is given by P bar cross E bar. Okay, what is P bar? It is the electric dipole moment. Okay, of a dipole, and E bar is the electric field. So this torque is vector product of P bar and E bar. All right, and we know the vector product is given by what? It is magnitude of first vector into magnitude of second vector multiplied by sine of the angle between two vectors. So if you see over here, this will be the angle between the two vectors. This angle is theta. Okay, so this is the direction of the dipole, right? Electric dipole vector is directed from minus q to plus q. and this is the direction of the electric field. So angle between them is theta. So the torque acting on a dipole in an electric field is Pe sine theta. Alright. So there can be a direct question on this thing also. Actually there was a direct question. Okay. Okay, after that let's talk about the next thing, and it's very important thing. So it is the electric flux. So what is electric flux? So let's say you consider some area and you take it in some electric field. So there is some electric field and you keep some area in that electric field. So what happens? Okay, so some electric field lines will pass through that area, and the electric flux is defined as the number of electric field lines passing normally, okay, passing normally through given area. Normally means perpendicular. So what is electric flux? It is number of electric field lines passing perpendiculars to the area. Okay, and how do we find it? So let's say d phi is the electric flux passing through this area. So what is this electric flux? So let's say this is the direction of electric field, okay, and this angle is theta. So your electric field is acting in this direction, and this is an area. So we know now that area is also a vector quantity. We have studied this in this chapter itself. Okay, so area is a vector quantity, and what is direction of area? The direction of area, it is given by a perpendicular drawn to the area. Okay, so direction of area is given by a unit vector drawn perpendicular to the plane of area. So if area is like this, direction will be like this. Okay, so d phi is the flux passing through this area. Okay, this area. So it is flux due to this electric field through this area. So it is dot product of the electric field and this area vector. Okay, so it is E bar dot ds bar. All right. So this is electric flux through some area, small area. Then next thing is the Gauss's law and its applications. Okay. So what is Gauss's law? What does the Gauss's law say? So Gauss's law says that the total flux through any closed surface, total flux due to what? Total flux due to the electric field through any closed surface is equal to algebraic sum of the charges enclosed by surface divided by epsilon naught. Okay, so that means if you take any closed surface, it doesn't matter what is the shape of that surface, and you have some charges, let's say q1, q2, q3, okay, inside that surface. So there will be flux due to all of these charges. Okay, so there will be electric field lines due to all of these charges. All right, so sum of all those electric field lines passing normally is what? It is the flux. All right, so there are electric field lines due to q1, there are electric field lines due to q2, there are electric field lines due to q3, radially outwards or inwards depending upon what? Whether the charge is positive or negative. Okay, if it is positive, radially outwards. If it is negative, radially inwards. So sum of the addition of all these electric field lines, okay, passing normally through this area, through this closed surface, is given by this thing, this integral. It is integral of E bar dot ds bar. So if you consider small area, we have seen it here. If you consider small area, then the electric flux through that area is given by what? Dot product of electric field and that area vector. Okay, so if you consider total area, what will be the electric flux? It is E bar dot ds bar. All right, so integral of E bar dot ds bar. Okay, then Gauss's law says that this flux is equal to what? The total charge enclosed by the surface. So here there are three charges, q1, q2, q3. So total charge q will be what? It is q1 plus q2 plus q3. Okay, so total charge enclosed by the surface divided by epsilon naught. All right, This is the Gauss's law, and there have been many questions on Gauss's law, okay, in NEET exam as well as in the JEE. All right, so this is an important topic, okay, and we have seen the applications of this Gauss's law in the 12th standard, okay. So what are the applications? So Gauss's law is used to find out electric field due to symmetric surfaces, okay, or symmetric bodies. So here, this is, let's say, first application, electric field due to a long straight wire. Okay, so you have a long straight wire, the electric field due to that wire, it is given by what? It is given by lambda divided by 2 pi epsilon naught r. Okay, so you find this using the Gauss's law. So derivation we have seen, and now it doesn't matter what's the derivation, but we have to memorize this formula. The electric field due to this long straight wire, it is directed. So first thing is direction. It is directed outwards, so it is perpendicular to this wire. Okay, it's directed like this. Let's say you take this point and you want to find out electric field due to this wire. So it is directed like this, okay, towards that point if it is positive charge, and if it is negative charge, it will be directed like this in opposite direction, okay. And what's the magnitude? So the magnitude of this electric field due to this long straight wire is lambda upon 2 pi epsilon naught r, where r is distance of that point, okay. So lambda is the linear charge density. So what is linear charge density? It is charge on this wire divided by length of the wire, okay. So lambda is linear charge density, so it is q upon l. All right, and let's draw r cap over here to show the direction, okay. So this is the electric field due to a long straight wire. After that, we have electric field due to charged infinite plane. Okay, you have infinite plane. What will be electric field due to that? So again, the electric field due to an infinite plane, it is given by sigma upon 2 epsilon naught, and it's directed, okay, towards that point if this is positive charge. So let's say this distance is r, and this vector from the plate, okay, towards the point is r bar, okay. So if you want vector, it is sigma upon 2 epsilon naught into r cap, okay. And what is sigma over here? So sigma is the areal charge density. That means it is charge per unit area of this infinite plate, okay. What is sigma? It is areal charge density, that is charge per unit area. All right, so this is simple, okay. And then we have the electric field due to uniformly charged thin spherical shell, okay. So we have a spherical shell like this, a shell, a hollow sphere, and that hollow sphere is uniformly charged. Then what is the electric field due to that shell? So if you consider a point inside the shell, then the electric field acting on that point will be equal to 0, okay. So if point is inside the shell, then the electric field acting on that point is 0. And if your point is outside the shell, then let's say if you have this point, okay, then the electric field is given by 1 over 4 pi epsilon naught into q over r square, where r is distance of this point from the center of the shell. So this charge distribution acts as if there is a point charge kept at center of the sphere, okay, or center of the shell. All right, so this is simple, and that's all for the theory of this chapter, okay. Now let us see some problems. Oh, where are the problems? Okay, so let's see some problems. So problem number 1, two charges A and B having charges plus q and minus q respectively are placed at certain distance apart and force between them is F. Okay, so we have two charges q minus q and they are kept at some distance away from each other. Okay, and force between them is F. Force between them is F. So what will be force? It is 1 over 4 pi epsilon naught into q times minus q over r square. Okay, then if 25% charge of A is transferred to B, so 25% charge from A is transferred to B. Okay, so from plus q to minus q we have transferred 25% of charge. Then force between the charges becomes, so this is very simple question. See, if 25% charge, okay, so 25 by 100 of q is transferred to minus q, what will happen? So charge on q will be how much? It will be 75 by 100, 75%, right? So now here you have some 100% negative charge and you are adding 25% positive charge to it. What will happen? The charge, positive charge will cancel out with 25% of negative charge and you will have 75% of negative charge over there also. So charge on A and charge on B becomes what? Equals to 75 upon 100 because we have transferred 25% of positive charge. So 75% of Q. So we can divide by 25 to the numerator and denominator. So we'll get 3 by 4 because 25 3s are 75 and 25 4s are 100. So 3 by 4 of Q. And charge on B will be what? Will be equal to, so because we are adding 25% positive charge, it cancels out with 25% of the negative charge. So how much of negative charge is left there? Again, it is 75% of minus q. Okay, so it's 3 by 4 of minus q. Very simple. And now what will be the force is the question. So now the force will be equal to what? 1 upon 4 pi epsilon naught, or k we can say. Now the charge is 3 by 4 times q multiplied by 3 by 4 times minus q over r square. So 3 times 3 is 9, 4 times 4 is 16. So this is 9 by 16 times 1 over 4 pi epsilon naught multiplied by q into minus q over r square. And what is this? This is F. Okay, the force in the earlier case, right? 1 over 4 pi epsilon naught into q into minus q over r square. Okay, so let's say force afterwards becomes F prime. Okay, so F prime equals to what? It is 9 by 16 times F. Okay, so 9 by 16 times F is the answer. Option C. Option C. So is it clear? Yes. Okay, then let's move on to the next question. The next question is, suppose the charge on proton and an electron differ slightly. Okay, so one of them is minus E, the other one is E plus delta E. So charge on electron is minus E and charge on proton is E plus delta E. If the net electrostatic force and gravitational force between two hydrogen atoms placed at a distance d much greater than atomic size apart is 0, then delta E is of the order of. Okay, so question is, you have two hydrogen atoms. Okay, charge on proton is E plus delta E, charge on electron is minus E. Okay, and the net force between those two hydrogen atoms is 0, then delta E is of the order of. So we have to find out order of magnitude of delta E. Alright, so yes, let us try to solve this. So you have two hydrogen atoms. So there is one proton, one electron. Charge on electron is minus E. Charge on proton is how much? It is E plus delta E. And then you have another hydrogen atom at some distance. Okay, so it's given that the distance is much greater than the atomic size. Okay, so you have this proton and and electron over here, minus E. Okay, so you have E plus delta E charge over here. So now see what will be net charge on a hydrogen atom. So it is E plus delta E minus E. Okay, so this plus E and minus E gets cancelled out. So net charge over here is delta E and net charge over here is also delta E. Okay, so it's like there are two positive charges having charge equal to delta E separated by this much distance. Okay, this much distance r. Okay, and it's given in the question that the net electrostatic and the gravitational force acting on these two charges is equal to 0. Okay, so sum of the electrostatic force plus gravitational force is equal to 0. That means what we can say is the two forces are same in magnitude and opposite in direction. So gravitational force is attractive. Okay, gravitational force will attract the two charges and electrostatic force will repel them. Okay, so we can say the electrostatic and the gravitational force, they are same in magnitude and opposite in direction. So F electrostatic is equal to F gravitational in magnitude. Okay, so which is 1 over 4 pi epsilon naught multiplied by delta E into delta E over r square equals to, we have G gravitational forces capital G into m1 m2, but mass will be equal, so m times m over r square. Okay, so this r square and r square gets cancelled out, right? And we are given that mass of hydrogen atom is this thing, 1.67 into 10 raised to minus 27 kgs. Okay, so what do we have? So what do we have is, okay, let's substitute the values. Okay, we want to find out what? We want to find out the excess charge, right? So this magnitude of delta E we want to find out. So it is delta E square multiplied by this thing is 9 into 10 raised to 9, and it is equal to, we know the value of G, it is 6.67 multiplied by 10 raised to minus 11, and multiplied by, we have m times m. What is m? It is mass of hydrogen atom. Okay, mass of hydrogen atom. This is 1.67 into 10 raised to minus 27. It's given. It is 1.67 into 10 raised to minus 27. And we have square of that because we have two hydrogen atoms. Okay, so then, and what do we want? We want the order of magnitude calculation. Okay, so this is of the order of 9 can be approximately approximate it to 10 because we want order of magnitude only. Okay, so this is 10 raised to 10. Okay, 9 is approximately 10, so 10 times 10 raised to 9 is 10 raised to 10, multiplied by we have delta E square, and on right side we have 6.67 into 10 raised to minus 11. So this 6.67 is approximately 10. Okay, we want order of magnitude only, right? So anything above 5 will approximate it to 10. Anything below 5 will approximate it to 1. Okay, so it is 10 raised to 1 multiplied by 10 raised to minus 11 multiplied by 1.67 will approximate it by 1. Okay, so we have 10 raised to minus 27 square, which is 10 raised to minus 54, right? Okay, yeah. So let's take this 10 raised to 10 on other side. What do we get? Delta E square equals to, this is 10 raised to minus 10, and this 10 raised to 10 on other side will become what? 10 raised to minus 10. Okay, or you can say it's 10 raised to 10 in denominator. So if you take it in numerator, it becomes 10 raised to minus 10. So 10 raised to minus 54 minus 10, that is minus 64, minus 10 is minus 74. Okay, it is 10 raised to minus 74, and this is delta E square. We want what? We want delta E, so it will be square root of that. So it is delta E is equal to what? Square root of 10 raised to minus 74. Okay, so that will be how much? 27, 37. Okay, so delta E is nearly I'm sorry of the order of 10 raised to minus 37. Okay, this should be the answer. So let's check. So it is option B. Okay, so simple. So yeah, this is simple. And now that students have evaporated, anyways, let's move on to the next problem. So next problem is two positive ions, each carrying a charge Q, are separated by distance d. Okay, so we have two ions, two positive ions. They are separated by distance d, and charge on them is Q. If F is force of repulsion between the ions, so two ions are repelling each other. Okay, the number of electrons missing from each ion will be. So how many number of electrons are missing from each ion? Okay, we know if electrons from atom are removed, it becomes a positively charged ion. Okay, E being the charge on the electron. So what do we have? We have two ions having charge Q and at distance d. And what do we want to find out? We want to find out the number of electrons missing from each ion. Okay, so how much will be the force between ions? It is 1 over 4 pi epsilon naught multiplied by Q times Q over R square, but R is equal to what? D. Okay, they are separated by distance d. So here it will be d square. Okay, and see, if you remove n number of electrons from an atom, the ion will be there. Okay, it will have charge equal to what? Plus n times E. Okay, because you have removed minus n times E charge from the atom. Okay, so the Q can be replaced by what? So this is equal to 1 over 4 pi epsilon naught into n times E multiplied by n times E over d square, and you want n, right? You want number of electrons. So let's take other things on other side. So what do we get? 4 pi epsilon naught d square will take on other side. Okay, into F is there. So it is F into 4 pi epsilon naught into d square. This is equal to what? N square. N into n is n square. E into e is e square. Okay, so this is equal to n square e square, and you want n, so you will take that e square also on other side and you will take the square root. So I will write it as n square equals to f into 4 pi epsilon naught d square divided by e square. Okay, and you want square root of that. So let's remove this square root. Sorry, let's remove the square and substitute square root on the other side. So it is f into 4 pi epsilon naught d square upon e square. So e square square root can be taken out. Okay, but it is in this option 4 pi epsilon naught fe square upon d square. Is this one? No, it's not this one. Here, okay, d square is in denominator. We have d square in numerator. So it is option C. Okay, option C is the answer. Okay, yeah. So let's move on to the next problem. Next problem is an electron falls from rest through a vertical distance h in a uniform and vertically upward directed electric field. Okay, so we have vertically upward directed electric field, sorry, like this. Okay, and an electron falls in that field. So there is an electron which is falling in this field. Okay, then the direction of electric field is now reversed. Okay, we reverse the direction of electric field keeping its magnitude same. Okay, so magnitude is suppose E, so this was E bar. What we are doing is we are reversing its direction. Okay, a proton is allowed to fall from rest. Okay, now we have reversed the direction. Okay, so this is, let's call it E prime. Okay, whose magnitude is equal to E, and now we are allowing a proton to fall in this field. So it is plus E charge, but its mass will be much more, right? Okay, proton is allowed to fall from rest in it through the same vertical distance h. Okay, so distance by which this electron falls is equal to distance to which the proton falls. Time of fall of electron in the comparison to time of fall of the proton is. Okay, so options are smaller, larger, 5 times larger, 10 times larger, equal. Okay, so actually even without solving this, we can say that time for electron should be much smaller because its mass is very small, so its acceleration will be much more compared to that of proton because they have same charge on them. So because mass of proton is much more, okay, mass of electron is much smaller, so the acceleration of electron will be much more. Okay, because mass is small, acceleration will be more, and therefore it will fall faster. So time required will be smaller for the electron. Okay, so smaller should be the answer, but let's solve this. Okay, but if this is an exam, you should think in this way only. You should reason like this, that acceleration of electron would be much more compared to acceleration of the proton, because proton's mass is much more compared to that of electron. All right, and therefore the time required for fall of electron would be what? Much smaller. Okay, then we have, yeah. So what is acceleration? So it is force divided by mass, because force is mass into acceleration. So force is E times E. Okay, so force on electron and force on proton is equal. because charge on them is equal. So E times E is the force and m is suppose mass, then acceleration will be E times E upon m. So if they are starting from rest, okay, if they are starting from rest, then we know that for this distance, this is the displacement, let's say. So h is the displacement, it is equal to ut plus half of at square is our formula. Okay, so for proton I can write u is equal to 0 for both, so it is equal to half of acceleration of proton into t square, t for proton square, and h is equal to, I can say, half of acceleration of electron into t for time for electron square. So what did I do? S is equal to ut plus half at square is our formula. Initial speed is 0. Okay, they are falling freely in that electric field. Okay, so we have h is equal to what? Half of at square. So for proton, I have put suffix p. Okay, so it is half of ap into tp square for proton, and for electron I have put suffix e. Okay, so for an electron it is half of a into t square, but I have put suffix e. So this is equal, since height with which they falls, sorry, height through which they fall, okay, it is equal, and therefore you can say the half factor also you can neglect because it's equal over here. So I can say ap into tp square, time for proton square, is equal to acceleration of electron multiplied by time for electron square. And now we substitute acceleration equals to this thing. Okay, E times E upon m. Okay, so for proton it will be E times E divided by mass of proton. Okay, this is the change. Okay, instead of m we'll have mass of proton multiplied by Tp square, and this is equal to E times E divided by, we have mass of electron, okay, into T squared. So this thing gets cancelled, this thing gets cancelled, and we wanted to find out time, okay, time for the electron to fall through that distance. Okay, so we want to find time for the electron. So let's take this mass on electron on other side, so it goes in multiplication. So I can write time for electron square is equal to mass of electron upon mass of proton multiplied by time for proton square, and if you take square root on both sides, you will get time for electron is equal to square root of mass of electron multiplied by, sorry, divided by mass of proton multiplied by time for proton. And here we can see that mass of the electron is very small. It is of the order of 10 raised to minus 31 kgs, and mass of proton 10 raised to minus 27 kgs, right? So 4 orders of magnitude difference is there. Okay, 10 raised to 4 times, okay, difference is there. So this will be, let's say, 1 upon 10 raised to 4 or something. So this is very small number, right? And therefore time taken by electron will be very small, because this is very small compared to 1. So very small compared to time for the proton. This is the answer. Okay, but as I said, you don't need to calculate all this, you can reason. Okay, like why, like what I explained earlier. Okay, since mass of electron is much smaller compared to mass of proton, the force on both of them is same because charge on both of them is same. Okay, the acceleration of electron will be much more compared to acceleration of proton, and that's why, since acceleration of electron is much more, it will take very small time. Okay, it will take much lesser time compared to that of proton to fall through the same distance. Okay, so need not solve this, okay, if you can reason. All right, so this was very simple question. Okay, so yes, let's move on to the next question. A toy car with charge Q moves on frictionless horizontal plane surface under the influence of electric field E. There is a toy car, it has got charge Q, and therefore if you keep it in electric field, it is going to get accelerated. Due to the force QE, its velocity increases from 0 to 6 meters per second in 1 second. Okay, so its velocity increases from 0 to 6 meters per second in 1 second duration. At that instant, the direction of electric field is reversed. Okay, so you accelerate a car and then you reverse the direction of electric field at that moment. The car continues to move for 2 more seconds under the influence of this field. The car keeps on moving. The average velocity and average speed of the toy car between 0 to 3 seconds are respective. Okay, so we want to find out its average velocity and average acceleration from 0 to 3 seconds. So when was it reversed? The direction of electric field, its velocity increases from 0 to 6 seconds in 1 second, and at that instant the electric field is reversed. Okay, so yes, we have a toy car, there is some charge plus q on this toy car. Okay, and it's moving. Okay, initially it is at rest and it is moving in the electric field now because there is some electric field. So let's say it goes till this point, okay, till this distance, all right, in 1 second. And there, what do you do at that point? You are reversing the direction of electric field. Okay, so at this point you are reversing the direction of electric field. Okay, so see here what happens. It gains some velocity. So initially u is equal to what? It is 0. At this point its velocity is something. Its velocity is this much, 6 meters per second. Let's call it, okay, v1. Okay, so at this point v1 equals to 6 meters per second. After that, it is allowed to move in this electric field, reversed electric field. So earlier it was getting accelerated, now it will get decelerated. Okay, so if the electric field is same, that means force acting on the car is equal, right? So acceleration, now the deceleration will be equal as that of what? The earlier acceleration. Okay, so what happens now? So now the speed of car will decrease, okay, and it will cover same distance, okay, in same time, and it will stop over here. So it stops at 1 more second. Okay, but see what is done. So it continues to move for 2 more seconds. So this car will stop over here. Okay, let's call speed over here v2 equals to 0. So car stops at this point. Okay, and then what will happen? So car is at rest at that point. Electric field is directed like this, so that electric field will push the car in this direction, reverse direction. Okay, so in 1 more second what will happen? The car will move in the reverse direction and it will come over here and it will attain same speed, same amount of speed. How much? Its speed now at this point will be how much? 6 meters per second, because it is moving through same distance. Okay, it's same acceleration for same time, so it is moving through the same distance. Okay, I'm sorry. So its speed over here, let's say it comes back, the car comes back, and its final velocity over there v3 equals to equals to what? 6 meters per second. Okay, so now you want to find out the average velocity and average speed. Okay, all right. So what is average velocity? It is the total distance covered divided by total time taken, right? So first we need to find out how much distance it will cover. Okay, so it goes from here to here, then from here to here, and from here to here backwards. Okay, so distance covered will be this much only. Okay, not distance covered, the displacement will be this much. Actually distance covered is much more. It goes from here to here, from here to here, and from there to, okay, in backwards direction it comes back and stops at this point. Okay, so let's find out how much is the displacement. So displacement is this much only, because this is starting point, this is the end point of total motion. Okay, so displacement S is equal to, so we can use S is equal to ut plus half at square. Okay, u times t plus half of a into t square. Okay, so t is equal to 1 second, because it covers that much displacement in 1 second itself. All right, and for that 1 second acceleration is constant. So how much is acceleration? It goes from 0 to 6 meters per second in 1 second. So we can calculate the acceleration. It is final velocity minus initial velocity divided by time. Time is 1. Okay, so 6 meters per second square is the acceleration, and u is 0. Okay, initial velocity is 0. So first term is 0. It is half of 6 into t square. So it moves from here to here in 1 second. So time is what? 1 second. Okay, so into 1 square. So 6 by 2 is 3. So S is equal to 3 meters. Okay, now what happens? So what is the velocity? It is equal to what? Distance covered divided by time taken. So it is equal to, so for entire motion also, it moves from here to here, then from there to there, and from there it comes back and stops over here. So total displacement is this much. And how much is the time taken? 1 second, 1 second, and for return journey 1 second, one more second. So it is 3 seconds. Okay, so it is 3 divided by 3, so 1 meter per second is the velocity. Okay, but what about the speed? So speed is total distance divided by total time. So that is, how much is total distance? So this distance is s plus s, and then it comes back, okay, through distance s. So s plus s plus s, okay, 3 times s, right? So it is 3 times s upon time is 3. So 3 times 3 is 9. S is how much? It is 3 meters. 9 upon 3. So it is 3 meters per second square. So this should be the answer. Okay, the option B is the answer. So yes, is it clear? All right, now I guess nobody is watching it. Anyways, let's see the next question. And the next question is, a square surface of side L meter, so we have the square, in the plane of paper is placed in uniform electric field, okay, acting along the same plane. Okay, the electric field is acting along the same plane at an angle theta with the horizontal side of the square. Okay, so it is at an angle theta with the horizontal side, with this side of the square. The electric flux linked to the surface in units of volt per meter is. So this is very straightforward question, and these kind of questions were asked many times. So what will be flux over here? So flux over here will be equal to what? 0. Okay, because what is flux? It is number of electric field lines passing normally through the area, passing through the area. Okay, and here area is like this, electric field lines are passing like this. Okay, so electric field lines are passing over the area. Okay, all right, they are parallel to the area. None of the electric field lines are passing through the area, and that's why the flux is 0. Okay, very simple. Okay, next question, and I can see it is similar to the last question. A square surface of side L meters is in the plane of the paper. Okay, you have a paper, and on that paper, so this is okay, this is regarding your question paper. Okay, so it is that square surface, they are saying it is in plane of your question paper, okay, of NEET, or it was AIPMT at that time, 2006. Okay, a uniform electric field E bar volts per meter is also in the plane of the paper. So again it's similar. Okay, and it is limited only to lower half. Okay, they are making it complicated. So the electric field is in lower half surface as shown in the figure. The electric flux in SI units associated with the surface is, so how much is the electric flux? So again, see, the electric field lines are passing over the area. Okay, they are parallel to the area. None of the electric field lines are passing through the area. All right, and therefore the flux must be equal to what? 0. Okay, so this is exactly similar, and like I said, the questions on electric flux are repeated. Okay, so there will be lots of questions on electric flux. Very often they are repeated. Okay, and the point is they are very simple. Okay, all right. Next question. 3-point charges plus q minus q and q plus q are placed at points. These are the points: x equal to 0, y equals to a, z equals to 0. X equals to 0, y equals to 0, z equals to 0. And x equals to a, y equals to 0, z equals to 0 respectively. Okay, so let's draw those charges at those points. So let's draw xyz axis. I will erase this 2007 from here. I'll make some space. All right, so you have xyz axis. Nobody's watching this. You have x-axis, y-axis, and z-axis. Okay. Oh no. Okay. So this is your z-axis, the x-axis, y-axis, and z-axis. Okay, and then you keep charges plus q, minus q, and plus q. So plus q is at x equal to 0, y equals to a. Okay, so let's say this my distance is a. Okay, and z equals to 0. So this is plus q charge. Then minus q is placed at x equal to 0, y equal to 0, z equals to 0. So that is your origin. So this is charge minus q at the origin. And then at x equal to a, y equal to 0, z equal to 0. So x equal to a. So it will be somewhere here. Y is 0 and z is 0. So charge is over here. So minus q. So the distances should be same. Okay, this is a, this distance is also a. And now it is plus q. All right. So the magnitude and direction of electric dipole moment vector of this charge assembly. So you want to find out the magnitude and direction of the electric dipole moment. So see, there are two electric dipole moments over there. One is because of this negative and this positive charge. The another one is because of this negative and this positive charge. How are they directed? We know the direction. Magnitude will be equal q into 2a. Okay, because this distance is a, this distance is also a. So this is the first dipole moment and this is second dipole moment, and you will have resultant of these two. Okay, so resultant of these two will be what? So if you take the parallelogram law of vectors addition, parallelogram law of vectors addition, so you complete this parallelogram, so resultant will be directed like this. Okay, so this is, let's call this P1 bar and P2 bar. Okay, so this is your P1 bar and this is P2 bar. So the P bar is resultant of P1 bar and P2 bar. So the magnitude of P bar will be equal to what? So the magnitude of P bar is P will be equal to square root of P1 square plus P2 square. These are magnitude of first vector square plus magnitude of second vector square plus 2 times the cos of 2 times P1 P2 into the cos of the angle between two. And how much is the angle between P1 and P2? It is 90 degrees. Okay, so cos of 90 degrees. Alright, so cos of 90 is 0. So this term is 0. Magnitude of P1 is equal to magnitude of P2 because this distance is same to as that of this distance. So how much is magnitude of electric dipole moment? It is q into 2a. Okay, so magnitude of P1 is equal to q times 2a. Magnitude of P2 is also what? Q times 2a. Okay, and let's suppose it is equal to P. No, let's suppose it is q into 2a only. Let's substitute that. So if we substitute that, what do we get? We get 2qa square plus 2qa square. 2qa square plus, can you see this? Yes, plus 2qa square. Okay, which is 2 times 2qa square. So you can take 2qa outside of the square root. Okay, so it is root 2 because it is in square root, it is 2 times 2qa square. Okay, so you are taking square, you are taking square root of the square of 2qa, so it comes out of the square root 2 times qa as 2 times qa. Okay, and so yes, which is the option. Oh, I did a mistake over here, right? I'm sorry for this. So how much is magnitude of dipole moment? It is q multiplied by distance between two charges. So it is not 2a. Okay, it is a. So I went by the formula because we take, generally we take distance between two charges as 2a. Okay, so here distance between two charges is equal to a, not 2a, because this point is at distance a. Okay, so it is q into 2a and q into a. So here also it will be q into a square. So this 2 will not be there. Okay, this 2 will not be there. So it is 2 times qa bracket in bracket qa square, and you take that qa outside. So it will be what? qa only outside. Okay, so square root of qa. All right. So there was a silly mistake, and okay, it will be directed along the line joining which points? Okay, so what are coordinates of this point? Coordinates of this point will be what? Z coordinates will be 0, x and y coordinates will be a and a. right? So it is AA0. So directed from 0, 0, 0 to AA0. Let's see root 2 QA, and in option A it is x equal to A, y equals to A, and z equals to 0. So option A is the answer. Okay, so thank God I realized my mistake. Okay, so such kind of silly mistakes can happen. Anyways, but again, nobody is watching this, doesn't matter, right? All right. So let's move on to the next problem. The next problem is an electric dipole is placed at an angle of 30 degrees with an electric field intensity of 2 into 10 raised to 5 Newton per coulombs. So you have an electric dipole placed at an angle of 30 degrees with electric field intensity. Okay. It experiences a torque equal to 4 Newton meters. The charge on the dipole, if dipole length is 2 centimeters, is okay. So this should be simple. You have okay. So if you keep a dipole in an electric field, what happens? It experiences a torque, and that torque is given by what? P into E into sine of theta, and P can be written as what? Q into 2A. Okay, where 2A is length of the dipole. So 2A equals to 2 centimeters is given. Okay, I will not make the same mistake I made in last problem. So at the beginning only I wrote that it's 2A equals to 2 centimeters, not A equals to 2 centimeters, right? Okay, then it is Q times 2A into E into sine theta, and you want to find out the charge on the dipole. Okay, that is you want to find out Q. So let's take other things on other side. So we have Q equals to tau divided by it is Q, sorry, not Q, 2A E sine theta, 2A into E sine theta, and let's substitute values. So this is a very straightforward question. So the electric field intensity is 2 into 10 raised to 5. Okay, so not electric field intensity. How much is it? Is at an angle of 30 degrees. Okay, electric field intensity, yes, it is there in denominator, and torque is 4 Newton meters. Okay, so torque is 4 Newton meters. 4 divided by, we have 2 times A is 2 centimeters. Okay, so it is 2 into 10 raised to minus 2 in meters, and then we have electric field, so it's there 2 into 10 raised to 5, and sine of theta, so theta is 30 degrees, right? Theta is 30 degrees. Sine of 30 is 1 by 2. Okay, so this 2 and this 2 gets cancelled out. Okay, then you have, all right, so 4 divided by 2 is 2, and minus 2 and 5, so you have 3. You take that in numerator, so it becomes what? It becomes 10 raised to minus 3. So the answer is 2 into 10 raised to minus 3 coulombs. So it is, yes, it is 2 millicoulombs, right? 2 into 10 raised to minus 3 coulombs. So 2 millicoulombs is the answer. Okay, yeah, again, let's move on to the next question. So a spherical conductor of radius 10 centimeters has charge of 3.2 into 10 raised to minus 7 coulombs distributed uniformly. What is magnitude of electric field at a point 15 centimeter from the center of the sphere? So you will not get a simpler question than this, right? You have a sphere, its radius is 10 centimeters, okay, and you have a point at 15 centimeters. That means it is outside of that sphere, and you know the formula of electric field, and you just want that the electric field at a point 15 centimeters, okay, from the center of the sphere. So yes, you have electric field equals to 1 over 4 pi epsilon naught into Q over R square. So simple, right? So substitute the values. This is 9 into 10 raised to 9. It's given over here. Okay, so generally it's not given because, so this thing, it is assumed that you will know this value. Okay, 1 upon 4 pi epsilon naught is 9 into 10 raised to 9. Okay, so charge is 3.2 into 10 raised to minus 7. So 3.2 into 10 raised to minus 7 divided by R square. What is R? It is 15 centimeters. Okay, so 15 centimeters, that is 10 raised to minus 2 meters, and we have square of that. So lot of calculations. 9 into 10 raised to 9 multiplied by, okay, so let's do this. So it is 10 raised to 9 and this is 10 raised to minus 7. So that means it is 10 raised to 9 minus 7, so 10 raised to 2 multiplied by, it's 3.2, and in denominator we have 15 into 10 raised to minus 2 square of that. So 15 square is 2 to 5. 15 square is, yeah, 2 to 5. 2, oh I'm sorry, 2, I'm sorry again, 2 to 5. It's okay, what's happening? We'll write it here. 2 to 5 multiplied by 10 raised to minus 4. Okay, so we have to divide this. Okay, so let's find out order of magnitude of this. So I can write this as 2.25 into 10 raised to minus 2, right? 2.25 multiplied by 10 raised to 2, I can write, and we have 10 raised to minus 4 over here. So it is 2.25 into 10 raised to minus 2. Okay, so we have E equals to 9 into 9 into 10 raised to 2 multiplied by 3.2 divided by, we have 2.25 into 10 raised to minus 2. Okay, so what I have done is I've written this as 2.25 into 10 raised to 2, and that 10 raised to 2 and this minus 4 becomes what? 10 raised to minus 2. Okay, so then this 3.2 divided by 3.2 divided by 2.25 will give me 1 point something. Okay, so this is nearly, you can say it is 3 by 2, so 1.5 or something. Okay, so something like that, 1.5 or something close to, I can say 1.5 or something, 1.45. Okay, then this 10 raised to 2 minus 2 I will take in 10 raised to numerator, so it will become 10 raised to plus 2. So we have 9 multiplied by 1.5 multiplied by 10 raised to 4. Okay, this 10 raised to 2 and this 10 raised to minus 2 taken in the numerator. Okay, so it has to be something greater than 10. Okay, 1 point something, let's say 1 point, okay, 4 or something. 3 into 10 raised to what? 10 raised to 5, because this will be, okay, 15 nines are how much? 135. Okay, so this is 135, 13.5 multiplied by 10 raised to 4, or I can say 1.35 into 10 raised to 5. So this should be the answer. So yeah, close to that, option B, because we have done a round figure calculation. Okay, so option B. And yes, in all other options it is 10 raised to 4, 10 raised to 6, 10 raised to 7. Okay, so they wanted us to do round figure calculations, right? So this is very straightforward question, but somewhat calculations. Okay, so there shouldn't be any question in this. Let's move on to the next one. a thin conducting ring of radius r is given a charge q. Okay, this ring has charge q. The electric field at center O of the ring due to the charge on part AKB, AKB is here, AKB is E. So due to this part, the electric field at center is E. Okay, so like this, let's say it is due to this much part only, AKB. All right. Okay, then the electric field at the center due to charge on the part ACDB, okay, of the ring will be. So we know that electric field due to ring at the center, how much is it? It is 0, right? Electric field at the center is 0, okay, because if this ring has, let's say, some positive charge, okay, if you take any point, okay, this is center, you take some segment over here, you will have segment in the opposite direction. So there will be electric field due to this segment, which is directed like this. DE, the electric field due to this segment will be directed like this. So what will happen? The electric fields due to this segment and this segment, it is equal in magnitude, opposite in direction, so it gets cancelled out. Okay, so you can consider segment over here like this. So electric field due to this segment and the electric field due to a small segment in the opposite direction like this, it gets cancelled out. Okay, so the net electric field at the center will be how much? 0. Okay, the question is, there is some electric field due to this section, okay, AKB at the center, okay, and that electric field is E. So how much would be the electric field due to this section? So what will happen ideally is, this section we can break in 3 parts, okay, apart from okay, I will use this color, from A to C. Then there will be a part from C to D, sorry, and there will be a part from D to B. So there will be some electric field due to these 3 parts, let's say. So the electric field due to A to C will get cancelled out because of electric field from B to D, okay, due to this part. Okay, so electric field from A to C, not from A to C, due to this part, okay, this arc AC, and electric field due to this arc BD, it is directed like this, okay, it's equal and opposite, so it must get cancelled out. And so if we consider this complete part from A to C to D to B, okay, ACDB, then electric field due to this part and this part is equal and opposite, and it gets cancelled out, and the net electric field in a ring is equal to 0. So this electric field due to AKB must be cancelled by the electric field due to part CD, okay, like this, and it will be directed, so it will have same magnitude as that of this electric field due to AKB and the opposite direction. Okay, so this must get cancelled out because of electric field due to CD, so it has opposite direction. So opposite direction is, this direction is from K to O, so direction of electric field due to CD will be opposite from O to K. So how much is the magnitude? What's the answer? Answer is, the electric field is E along OK. Okay, yeah, this is the answer. All right. Okay, so let's move on to the next problem. The next problem is another problem on the electric flux. The electric flux, what is the flux due to a cube of side A if the charge of Q is at one of its corner? So this question is there in NCERT also. Okay, so this is straightforward question from your NCERT. All right. So you have a cube like this, okay, and you keep a charge over here, okay, at one of the corners of this cube. So how much would be the flux? So correct way to think about this question is, what you can do is, so you have to enclose this charge in order to apply the Gauss's law. So what will you do? So you can draw cubes like this. You will draw this another cube, okay. So then I will draw another cube like this, and another cube like this. So now how many cubes do I have? I have 4 cubes till now, okay. And is the charge enclosed? No. So if I keep similarly, if I keep 4 cubes over here, okay, now see, this charge was at one of the corners of this cube, okay. So we started with this cube, and what I'm doing is I'm building, okay, I'm building a building using cubes. So I'm keeping some other cubes like this, I'm arranging them, okay. So now this charge is half enclosed, okay. So if you keep 4 more cubes like this, so let's use different color because we will not be able to see it otherwise. So I keep 4 more cubes, okay. So this is one, this is second, okay, this is third, okay. Bear with my drawing like this. Drawing is a difficult thing, right? It's an art. So I'm not good at it anyways, but I have kept 4 more cubes like this. So now you can see this charge is there. Okay, so that charge was at one of the ends of this cube, and what you have done is you have kept 3 cubes side by side, and then you have kept 4 more cubes, and now the charge is enclosed totally. So for this assembly of 8 cubes, the charge is at the center of this assembly. Okay, so how much will be the total flux out of those 8 cubes? The total flux will be Q upon epsilon naught, because the flux through any closed surface is Q upon epsilon naught. So how much will be flux through one of those cubes? So flux through one of those cubes will be what? It will be Q divided by 8 epsilon naught, because Q upon epsilon naught is flux through this 8 cubes, okay, kept like this, and therefore flux through the cube with which we had started with, okay, that is here where the charge was at one of its corners, okay. So flux through that is Q divided by epsilon naught, sorry, Q divided by 8 epsilon naught. So flux through one cube equals to what? Q upon 8 epsilon naught. So option B is the answer. This is a direct question from NCERT. Yeah. Hi, Shakti. Okay. So is it clear? Since nobody is there, nobody will answer. So I guess it will be clear to who will watch it afterwards. Okay. Let's move on to the next problem. The next problem is A charge q is enclosed by a Gaussian spherical surface of radius r. If the radius is doubled, then the outward electric flux will be. So flux will not change, right? Flux remains same. Option C is the answer. Why? So you have this surface and you enclose a charge using that surface, okay, with that surface. So how much is flux outside? So flux outside, okay, is q upon epsilon naught. So now, what is flux? The number of electric field lines passing normally through a surface. Then you double the radius. Again, what will happen? All these electric field lines which passed through this sphere, they will pass through this sphere now. Okay? Yes. So flux will remain same, and that's the answer. So a very, very straightforward question, and this is the answer. The flux remains same, doesn't matter if you change the radius. So as long as the charge is enclosed, the flux remains same. Okay. So yes, this should be understood because this is very, very straightforward. So let's move on to the next question. The next question is a hollow cylinder has a charge q coulomb within it. If phi is the electric flux in units of voltmeter associated with the curved surface. So flux through the curved surface is given as phi. The flux linked with the plane surface A, okay, in units of voltmeter will be. All right. So flux through this surface, the curved surface is given. Flux through this part is asked. Okay. So yes, there is q upon epsilon naught in the answer. So how much will be total flux? So total flux, okay, due to a charge which is kept inside this cylinder is equal to q upon epsilon naught. So how much is total flux? It is flux through surface A plus flux through surface B plus flux through surface C. It is q upon epsilon naught. And it is given that flux through surface B is how much? It is phi. Okay, so phi B is phi. And we can say flux through A and flux through C. It is similar because area of this surface and this surface is similar. Okay, so flux through A equals to flux through C. Okay, so let's substitute that. So in place of flux through C, I will substitute flux through A. So it is phi A plus phi B is equal to phi plus phi C is equal to phi A, and that is q upon epsilon naught. Then you can take this phi on the other side. So you get phi A plus phi A 2 times of phi A equals to q upon epsilon naught minus this phi, and then you can take 2 on the other side, so it goes in denominator. Okay, so it is q upon epsilon naught minus phi divided by 2 is the answer. So option D is the answer. Okay, yeah, there is nobody to reply. All right. The charge q is located at center of a cube. The electric flux through any phases. So again, this is a straightforward question directly from NCERT. So you have a cube, it encloses some charge, okay, and it is inside the cube. So there are 6 faces of cube. So total flux, we know it is charge enclosed divided by epsilon naught, and therefore flux through a surface is equal to q upon 6 epsilon naught, because flux through 6 phases is q upon epsilon naught. Flux through one phase will be q divided by 6 epsilon naught. Okay, so that should be the answer. So is there such an option? Let's check. It is pi. Okay, you are multiplying with 4 pi in denominator. So 4 pi in denominator, 4 pi in numerator. You are multiplying and dividing by 4 pi. So this option B should be the answer. Okay, very simple. Next question. A hollow metal sphere of radius r is uniformly charged. Hollow metal sphere. Okay, a spherical shell. The electric field due to sphere at distance r from the center. Okay, so yeah, this is straightforward. Decreases as r increases from small r is less than capital R, and for r greater than capital R. Okay, so increases as r increases for smaller less than capital R and smaller greater than capital R. 0 as r increases for smaller less than r, decreases r as r. This is tongue twisting. Okay, increases for smaller greater than capital R. Okay, so option C should be the answer, right? The electric field due to a hollow spherical shell is 0 inside, so it is 0 as r increases for small r less than capital R, where capital R is the radius. Okay, so it is 0 inside, and it decreases as r increases, small r increases, that is the distance increases for small r greater than capital R. So outside of the hollow spherical shell, the electric field goes on decreasing. This is the answer. Okay. Next question. Two parallel infinite line charges with linear charge densities lambda coulombs per meter and minus lambda coulombs per meter are placed at a distance of 2r in free space. What is the electric field midway between the two line charges? So, a straightforward question. Once again, most of the questions were straightforward. You have two line charges, two parallel infinite line charges. Okay. Then the linear charge density on first one is lambda, on second one it is minus lambda. Okay, so minus lambda. Then they are at distance of 2r. So they are at distance of 2 times r in free space. So question is, what is the electric field midway between the two line charges? So if you take some point over here, what will be the electric field at this point? So the answer is simple. The electric field due to the first line charge is directed like this. Electric field due to second line charge is directed like this, because first line charge has positive charge on it, so electric field is outwards. Okay, perpendicular to the line charge, but it is directed outwards. Okay, the second line charge has negative charge on it, so electric field is inwards. It is perpendicular to line charge, but it is inwards. But magnitude will be same. So how much is magnitude? Let's say this is E, this is E, or let's call it E1, this is E2. Okay, so the magnitude of E1 is equal to magnitude of E2, and we know it is lambda upon 2 pi epsilon naught r. Okay, so the net electric field will be vector sum of the two, and because they are directed in same direction, so it is lambda upon 2 pi epsilon naught r plus lambda upon 2 pi epsilon naught r, sum of the magnitudes. Okay, so which is 2 lambda upon 2 pi epsilon naught r. So 2 gets cancelled out, and your electric field will be what? Lambda divided by pi epsilon naught r. So this is the answer. So lambda upon pi epsilon naught r is the answer. Which option? Option D. Okay. So this is simple. Yes. Let's move on to the next question. So yeah, there is no next question. So we finished all the questions that we wanted to discuss today. Okay. So there is nobody to discuss. That's another thing. Anyways, let's stop at this point. So tomorrow, maybe we'll start with the next chapter, electric potential and capacitance. Okay. So let's end it here.